Hello, this is Pat Kelly. Okay, so what they've got for us here is a differential equation and an initial condition. They're asking us to find the particular solution to this differential equation, given that condition. Okay, so let's get started. And it definitely looks to me like it's going to be an exact differential equation. I can see that because my dx, the factor in front of that, looks like a nice capital M. The factor in front of the dy looks like a nice capital N. But I'll tell you, the directions didn't specify that it's an exact differential equation, and they didn't even tell us to verify, but I always feel a little bit better if I know. Is it an exact differential equation? You can do some quick checking in your head. The partial derivative of m with respect to y, right, that's just going to be 2x. And that's going to blank out to 0. And you compare that to the partial derivative of n with respect to x. So these two guys will blank out, and the derivative is 2x. 2x equals 2x. I feel good. I feel good that I know it's an exact differential equation, because then I know my setup here, my routine for finding the answer works. And the routine is that we look for this little f of xy by doing some integration, and I hope this rings some bells for you. And you can integrate either m with respect to x, or you can integrate n with respect to y. It's a toss-up here. I think I might grab the n and integrate that with respect to y. So if I go ahead and integrate this, I was just thinking I'll grab orange for you there. This is where I'm grabbing my n from. 2y plus x squared plus 1. And I'm doing that full integral with respect to y. All right. Okay, so let's do that integral here. This first term is just y squared. This second term, integrating with respect to y, that's really just a constant. So plus x squared and y to the 1 power. And here's another constant, plus 1. I'll just write it as plus y, because you throw in your y to the 1 power there as well. Okay, that's good. But you also need to remember, if we just integrated with respect to y, there could be more of an expression involving x, so we tack on a plus g of x. It's kind of like when we used to tack on our our constant of integration, but here it's not necessarily a constant, it could depend on x. Okay, so this expression here is my f of xy, okay? Just want you to see this. F of xy is all of this, because I'm going to slip down to the next line here. And in order to get a firm handle on what g of x looks like, I actually need to take this f expression and differentiate with respect to x, a partial derivative of this f of xy function. So I'm looking at what I squigglied over here, and I'm differentiating it with respect to x. So that blanks out to 0. This second term looks like a 2xy. The third term, differentiating with respect to x, is also 0. And that last term, differentiating that with respect to x, makes g of x become g prime of x, okay? And we do that because, I'll switch colors for you here again, is that must equal m, that capital M that we labeled at the beginning of the problem. So that has to equal, what was my m, 2xy minus 9 x squared. And then you look for the balancing act here between these two expressions, the two xy's on each side already, so it's just a matter of the g prime of x must equal 9x squared, okay? I think I'm going to need a little bit more room for the next couple of steps, so let me slip over here, grab a different color if it helps. I now know, I'll say, so g prime of x has to equal that minus, make sure you catch your minus signs if they're there, minus 9x squared. What that allows us to do is get an exact expression for g of x, because what I'll do is anti-differentiate. So if I'm anti-differentiating this, the x squared bumps up to the 3 power, and then divide by 3, so minus 3x cubed. Okay? All right, that's good, because now, let me slip over here. Now I know what my general solution looks like. General solution. It's your f of x expression. Here's maybe the best place to look at it is the squiggled. It's all of this, but I now know what g of x is. That's what we just worked out. And that's all on the left-hand side of an equation, y squared plus x squared y, grabbing everything that was squiggly underlined, plus g of x, but that's actually a minus 3x cubed. And that's the left side of an equation, and the right-hand side is some constant, just c. We don't know what it is. Not yet. We don't know what it is for the general solution. For the particular solution, what we do is use that initial condition. Remember from the beginning of the problem, they gave us y of 0 equals a minus 3. So when we know that y of 0 equals a minus 3, we use that in the general solution right up above in order to find the exact value of c. And I hope you're remembering with these initial conditions, the way that you read them is that inside your parentheses, even from way back when we learned functions, that's your argument, that's your input, that's the x that we're going to have here and here, whereas the minus 3, your output, that's what we're going to have in each of these places for y. Okay? So that's what I'm doing in this next step. My y squared, but I'm putting a minus 3 in there, plus x squared, but x is 0, so 0 squared times y, it's your minus 3. Put parentheses around the 0 even so you can line things up, plus the y, and y was the minus 3. And where was I then? Minus 3 times x cubed, but x was our 0, so 0 cubed, and that equals the c. And what that does is allows us to get the value of c. So what are we going to end up with here? 9 plus 0 minus 3 minus 0 equals c. So c equals 6, I guess. That's good. And what color for our final answer? That means our particular solution is your general solution, but you now know the exact value for c. That's going to be our 6. So I'm looking right here at y squared plus x squared y plus y minus 3x cubed equals 6. Whew. That's the particular solution, okay? A bit of work, but you feel good when you get the right answer. So go get some right answers on your own.